Today we're going to go through the exam style questions for Unit 3, Use of Electromagnetic Waves in Communication. So question 1, electromagnetic radiation from the Sun is detected on Earth. Earth is 150 times 10 to the 9 metres from the Sun, and what speed do all electromagnetic waves travel at? So this is one you just need to learn. Is 3.00 times 10 to the power of 8, so that's a small 8 up there, meters per second. So in class sometimes we write meters per second like this, but this has already given it to you as meters seconds to the -1. They mean the same thing. Part B, the intensity of light from the Sun at the Earth is 1,400 watts per meters squared. Calculate the value of K for the Sun. So we need to use the equation I equals K divided by R squared here, and we're going to need K, so we'll rearrange our equation. So what I would do to rearrange this equation is I would times both sides by R squared, so that means you get K times R squared is equal to K, I times R squared is equal to K. And what we're going to do is write down what we know from the question. So we've got this here, which is our intensity, so that's I, watts per meters squared, and then we also need R somewhere. So R is our distance of Earth from the Sun here. So it's 150 times 10 to the power of 9. So to get our final answer for K, we need to do both of those numbers. We do 1,400 times, but this is important to get you right. I would use brackets. Your 150 times 10 to the 9, that has to be squared, okay? So if you get a different answer, it's probably because you've forgotten to square it. And if you type that into your calculator, you get K equals 3.15 times 10 to the power of 25 watts, okay? It's going to give you a really big number. Part C, calculate the intensity of light at Mars, 230 times 10 to the 9 meters from the Sun. So this time our R has changed, but I believe our I is still the same. Oh no, we're calculating the intensity. So what we're going to do here is we're going to use our original equation, I equals K divided by R squared. So we're going to use the K that we calculated in our last question. So K is going to be 3.15 times 10 to the 25. So we just calculated the K of our Sun. And then we're going to divide it by our new distance, 230 times 10 to the 9, but we cannot forget to square it. So if you type those into your calculator, you should get 600 watts per meter squared. So that's a smaller number than the intensity of the Sun on the Earth because it's further away. If we go on to part D, a scientist studies light from the Sun at a wavelength of 300 nanometers. What region of the electromagnetic spectrum is this light in? So that's something you need to remember, which nanometers of wavelength correspond to which part of the electromagnetic spectrum. And for this one, it's ultraviolet. Okay, so that's the part just next to our visible light spectrum, but a slightly shorter wavelength. And E, explain the effect of this wavelength on how we can use light in different applications. So a short wavelength has a high energy. So your first point here would be a shorter wavelengths have higher energy. And we can use this for specific effects. It can be directed for specific effects. So a longer wavelength can be diffracted more easily. And they have a larger range for communication without being specifically directed. So there we go. So to summarise, our shorter wavelengths have a high energy and we can direct them to get specific effects, but our longer wavelengths are more easily distracted and they've got a larger range for communication without having to specifically direct them.